This is the SNAP 2013 tutorial for the supports design search tab. And this allows us to find an optimum search, to find an optimum design for the wall, or a really good design that's hard to beat. Think of it like that. But we're just going to design in this video just the upper wall, and then the next video we'll design the lower wall, since these are kind of time consuming to do. Anyway, the first box that you see are the search options. So this allows us to search for the height of the wall. Say something like this, and we can allow the height of the wall to change from 5 to 20 feet at a resolution of 0.5. And so if we have this, if we change the height of the wall, what it will do is it will automatically excavate back to the previous point on the slope. So we need to make sure that we don't want to just excavate clear back to this point here, because then we wouldn't even need any wall at all, if we just cut the whole slope off. So let's go back to the slope tab and show that I entered a point here to say that it's only allowed to excavate back to this location. So if the wall gets shorter, it'll cut it back to here rather than all the way back to there. Just as an example. I'll go back to the supports tab, and what I did was first I saved the original design, and what this does is it tells me the original design had a factor of safety of 1.55 with a price of 1.4 million, and it fills in all of the variables here. So if I click the wall batter angle, I'll see that the original design had a wall batter angle of 10, but I'm going to allow it to search for wall batter angles from 0 to 40 degrees at a resolution of 1 degree. And you'll see there's a factor of safety here, and this is the minimum factor of safety for static loading, and I can set its value. I could also specify a minimum factor of safety for seismic loading, and it would require all of the designs to meet a factor of safety of 1.1 as well. But that would require an extra calculation. It's got to do one for the static case and one for the seismic case. And then I can also make sure that every staging cut has a factor of safety of at least 1. But that increases the search time because it has to go through every staging cut and calculate what is a factor of safety to make sure that they're all above 1. But in this case, those staging cuts are not very critical, and the seismic case I think was 1.3, and we can see that the factor of safety for the static case is 1.55. So the static case is the most critical here. If you pick one that's not the most critical, then it could, like if we designed it for a factor of safety for seismic of 1.1, it probably would fail in the static case if we didn't include that. So that's why it's good to include, if you want to make sure you can include all 3. Otherwise you can just include 1 and then run the report and make sure that everything passed. If it didn't, you can come back here and design, you can include both static and seismic. And anyway, we'll go ahead and design for the length of the nail from 5 to 40. The spacing, horizontal and vertical, we'll leave them the same from 2 to 10. We'll include an inclination angle. But I also want to allow the nails to fan. So I'm going to go back to the nails here, and I'm going to allow them to fan the nails. And I'll just put in the fan angle right now to be 15. And I'm also going to allow the nails to be cropped if the T-nail forces are shortened. So I'm going to crop that to the nearest foot. So I'll allow those designs there. Now go back to the design tab, and now it allows me to select to search for a fan angle as well. Otherwise it'll just leave it at 15 degrees, which is the original design. So I mean 45, but it wasn't used. So I'll allow this fan angle to go from 4 degrees minimum to 45 degrees maximum, resolution of 1. And I'll also do the cantilever distance, and I have to scroll over here to see it. It's from 1 to 3. And the drill hole diameter will be from 6 to 12 inches. And then the bar number, it'll be from 3 to 18. 18 is pretty high, but well, I'll just allow it to go up that high. I'm sure it won't pick it. And then resolution of 1. And we'll just use a factor safety of 1.5. So we're going to design on all of the variables and just see if it can beat this current design. And of course it's really not fair because we're allowing it to shorten the height of the wall and things, so it doesn't do anything against the engineer that designed this particular wall. It's just saying that we're going to allow a few more constraints than maybe the engineer was allowed to have. So I'm going to click search, and if I leave the mouse over, well, you can see that the search button just changed to cancel. So at any time I can click that cancel and stop the search and go back and change things and start it again. Or if I think it's found a pretty good design and it's probably not going to find a better one, I can just go ahead and stop it and use that particular design. But sometimes you never know. If you just let it run for another minute or two, sometimes it can save $2,000, $3,000, or $4,000 off the design, so it might be worth it to wait. And if you leave the mouse over this cancel button, you can see the status bar at the bottom. It will tell you the progress of the search, and it says it's collecting orthogonal observation 15 of 45. You know, and so it's about a third of the way done. And what it means by orthogonal observation is it's designing a wall with, say, the minimum wall height, the minimum batter angle, the maximum nail length. You know, so it uses minimums and maximums from each of the ranges and kind of gets the corners of the hypercube. You can think of it like that. It's filling those out with and it doesn't take every possible combination, just a small subset of those. So in this case, probably taking 22, and now you can look at the bottom. It says it's collecting random observation 29 of 45. So what it's doing is it's generating a random wall height, a random batter angle, a random nail length, and then it's designing a wall like that, and then it's calculating what is the price, what is the factor of safety of this random design. And so what that's doing is the orthogonal designs get the corners of the cube, and the random designs fill in the interior of the cube that it's of the hypercube that it's searching. So then what it does after it collects all of the observations is it uses artificial intelligence to try to figure out what is the best design. So it's not exactly a search technique, but it is a search technique in the sense that it's copying how a human thinks, or how an engineer would design a wall based on experience. And so that's what it's doing now, is it's simulating the scientific method. So first it collects a set of observations, then it figures out what are the relationships, the causal relationships between the parameters. And in other words, it's figuring out theories. Like it's figuring out the theory that the nail length, when I increase the nail length, the price goes up and the factor of safety goes up. But sometimes when the nail length is really long, I increase the nail length and all that happens is the price goes up, but the factor of safety doesn't improve. So it figures out all of these things, and then it says, like, when I have a low batter angle and I increase the nail length, or I have a low inclination angle and I increase the length of the nail, that has a different effect on the factor of safety than if I had say a short nail, or I had the same length of nail with a large inclination angle. So it's generating all of these theories and trying to figure out where are the causal relationships. Then what it does is it generates a hypothesis, and then it predicts that the hypothesis that it generates is actually it thinks this is the best wall design. And then I'm going to predict what is the price and factor of safety of that wall design. And when it does that, it then tells the system to go ahead and build that wall in simulation and calculate what the price and factor of safety was. Then it compares its predicted values, the prediction with the actual result. And if they're different, then it goes back and figures out, oh, I need to rethink my theories. I need to figure out, I need to change how I'm thinking about this problem, and then it goes and generates another hypothesis of what its best design was. And so it just keeps repeating this as it's until it can find the best design. And it's just finished the design now, and what it's done is, I'll just temporarily hide the user interface here, is it's found a design with a short nail, a short wall with just a single nail. So if I go back here, I can look at the SNAP design, and it did a 5-foot wall with a 0-degree batter angle, a 16-foot long nail instead of 30-foot, at a 10-foot horizontal spacing, at a 34-degree inclination angle, with that cantilever distance, drill hole diameter of 6, bar number, size is 14, and it got a factor of safety of 1.51. The price was down to $264,000 from $1.5 million, which saved us $1.2 million, which is an 82% savings on this wall. And it took 46 design evaluations for it to find this solution out of a possible, and I don't know if I can count all of these zeros, but it would be 6.5 trillion. Looks like that many total possible designs. And it found the design in 2 minutes. But if we did a brute force method, automatically calculating the price and factor of safety for each of the possible, 6.5 trillion wall designs, it would take about 650,000 years to exhaustively search all of the designs and come up with this solution. So anyway, let me go ahead and I usually click load snap just to make sure it loaded the most current version, but it already is loaded. And for the next video, we will design the second wall.